Hi there, folks. Today we're looking at systems of quadratic equations. These are just like any other system of equation that we've solved before, except now they'll involve quadratic equations as well, which means as we start to solve these things, we're going to see that we're solving quadratics, and it's going to end up having to be either solved by factoring, completing the square, or the quadratic formula, okay? So that's really the main difference, okay? We still approach it the same way that we normally would. So just a quick refresher here, if I look at these first two, these are set up for just a regular old system of equations, the kind we've been solving forever. And so if I look at this first one, it's set up nicely to solve this by substitution. Notice right here, y equals this whole thing. So that means I can plug that in for y in the second equation. So here we go. Instead of y, I've got a 2x minus 1. I distribute. I combine like terms. And now I finish solving this thing. I'm going to add the 3. And divide by the 7. And of course, I'm not done. I still have to plug this thing back in. So after I get the x equals 1, I need to find the y value also. So I need to plug it back into one of these guys. If I plug it into this guy, I get something like y equals, let's see, that's going to be a 2 minus 1, which is also a 1. So it's 1 comma 1. I write the answer as an ordered pair. Okay? If I look at the next one, same kind of thing. This one is set up nicely for solving by elimination. In fact, if I add these together exactly the way they are, the x's are going to cancel out. So if I add these up, that gives me a 3y equals. Over here, I get a 15. The x's cancel out. I divide each side. So I get y equals 5. I'm not done yet. I have to plug that 5 back into one of these equations. Let's say I plugged it into this one up here. And then I have to subtract that 10 from each side, divide by the 2, and I get a negative 2 for my x value. So let's see, that's going to be a negative 2, 5. All right? So remember, when we're solving a system of equations, we use substitution or elimination to get one of the variables. Then you got to plug it back in to get the other variable. All right? So not really much difference here. With solving systems of quadratic equations, I tend to stick with substitution. That's not to say that you can't do elimination, all right? But it's problematic, and it's problematic because we have x in two different places, all right? And so, like, if I looked at something like this guy, if I tried eliminating x here, trying to solve by elimination, let me just show this off in a little thought bubble. The reason this is tough is that if I leave that first one the way it is, if I were to multiply that second equation by a negative, giving me a positive x and a minus 2, all right, what happens is I go to add these up, the x's here are going to cancel, but I still have an x squared, okay? Now, this one will work out okay because the y's end up canceling, but the idea here is that with quadratics, because I have an x squared and an x, it kind of splits my x's up in a funny way, which means even when I try to eliminate x, I might still end up with an x because of that x squared, okay? If you have a quadratic and a linear equation, the variable you would want to eliminate would be the y variable, all right? And so for our purposes, it just becomes much easier to kind of stick with substitution most of the time, all right? And so for this one, these are already set up nicely for substitution. Anyway, I've got y equals this whole thing right here, which means I can plug that in for y in the second equation. So here's what that looks like. If I plug that in for y in the second equation, that gives me an x squared minus x minus 2 equals the negative x plus 2. Well, now I can go ahead and solve this thing. I can solve for what's left. I can solve for the x. But because it's a quadratic, I have to use my quadratic methods, all right? I have to use factoring, completing the square of the quadratic formula. Remember, I always check factoring first. So I'm going to add the x to each side. I'm also going to subtract that 2 from each side. Remember, to do factoring, I have to have this thing set equal to 0. So that gives me an x squared minus 4 equals 0. And now I solve by factoring. So I factor this thing. This factors into an x plus 2 and an x minus 2. That is a difference of squares. And now I can set each factor equal to 0. So I solve each of these. And yeah, you could probably solve, wow, that's a terrible looking 2. You can probably solve each of these in your heads, which is fine. So I've got x equals a -2 and x equals a +2. And this is where students tend to fall apart when it comes to systems of quadratics. As I look at this, students will stop here and go, oh, there we go. I've got a -2 and a +2. Let me just write that as an ordered pair, -2, 2. But what I have here are two different x values, all right? And just like every other system of equation that I've ever solved, once I solve for one of the variables, I get something like x. I have to plug it back in to get y, all right? The difference here is I'm going to get two different answers. I'm going to get two different ordered pairs, which makes sense because with quadratics, a lot of times I got two different answers. So with a system involving quadratics, shouldn't I get two different answers also? Well, that's going to be two separate ordered pairs, okay? And so I just have to be really careful in terms of staying organized here. Let's plug the -2 in, and you can plug it into either equation. If we have a linear equation, it's probably going to be easier to plug it into this guy, okay? So if I plug the -2 in there, that gives me a +4. So that's one of my ordered pairs. So that's just one of my answers. I also have to plug the +2 in and get my other answer. And again, it has to be the specific ordered pair. That first x of -2 goes with that specific y value. The y value of +2, if I plug it into that linear equation again, gives me a 0. And again, it's that specific ordered pair, all right? And when you think about it, it makes sense because if you were to think about the graph of this thing, let's just think about the graph. If I looked at the graph of this thing, I've got a parabola that opens up and has a y-intercept of -2. Kind of looks like something like this, okay? And then I have this line that has a y-intercept of +2 and a negative slope, kind of looks like this. Look at that. Of course it's going to have two values. They cross at two different spots. I have one value over here that must represent my -2, 4. I have one value over here that must represent my 2, 0. And again, I just drew a quick sketch to visualize this thing. That graph is not super accurate, but I could graph these accurately. And if I did, I would see the intersection at these 2 points. And remember, system of equations can be solved by graphing. This could be solved by graphing also. It's just not typically the best method, okay? But again, I get two x values. I have to plug each of them again and get y values to go with them, okay? Just like I always have for system of equations. If I look at the next one, same kind of thing. I've got a quadratic and a linear equation. I'm going to use substitution here. And if I use substitution for this one, well, right here, y equals this thing, so I can plug that in for y in the second equation. So it looks like this. X squared minus 6x plus 10 equals the 4 minus x. And now if I want to solve this quadratic, I always check factoring first. So I'm going to get this thing set equal to 0. So I'm going to add the x to each side. I'm also going to subtract the 4 from each side. So I get x squared minus 5x plus 6 equals 0. I build a bridge and I factor this thing. This one factors into an x minus 3 and an x minus 2. And now I set each of these equal to 0. And I solve each. And again, yeah, I know most of you can kind of skip this last step and do it in your head. That's okay. But once again, what I get here is two different x values, okay? This has nothing to do with y so far. I have two different x values because I have two different solutions. I have two different ordered pairs. I have to find each of those ordered pairs, okay? So back up here, let's see. I put the 3 in. And again, use the linear equation. It's way easier to plug into, okay? So 4 minus 3 is a 1. So that's my first ordered pair. And then I plug the 2 in. Once again, 4 minus 2 is a 2. That's my second ordered pair. Okay? I get two different points of intersection, two distinct ordered pairs. Okay? If I look at this one, this time it's a system of quadratics, and they're both quadratics. But again, it doesn't really make that big of a difference. Here, we could maybe eliminate x, but it would have to be a really special set of equations to do that. We're still in that same boat where if we eliminate the x squareds, I might be left with the x's. Or if I eliminated the x's, I might be left with the x squareds. So x isn't truly being eliminated. All right, that's why we try to avoid elimination. If you're going to use elimination, try to eliminate y. All right, The best bet here is to always just use substitution, though, all right? And so if I look at this one, once again, substitution is set up really nicely. Y equals that thing, so I plug it in for y in the second equation, okay? So let's see, that's a negative x squared minus 2x minus 7 equals a negative 2x squared minus 6x plus 5. And once again, if I'm solving a quadratic, I want to set it equal to 0 first because I always want to try solving by factoring first. I'm actually going to add that 2x squared to each side. Add the 6x to each side. And subtract the 5 from each side, okay? So I'm going to move everything over to the left here. Let's see, that gives me an x squared plus 4x minus 12 equals 0, all right? And so now I build a bridge. I factor this thing. This guy's going to factor into an x plus 6 and an x minus 2. And now we set each factor equal to 0. So here I subtract the 6 from each side. Here I add the 2 to each side. So I get my two x values. X equals a negative 6 and x equals a positive 2. Once again, I'm not done, all right? I have to go back and plug each of these in. I have the x values. I need the y values that go with them, okay? And again, those x values represent two distinct ordered pairs. So I'm going to plug the negative 6 in. And really, neither of these equations looks great. Even though the first one might look simpler, and that's probably the one I would plug it into, most of you would probably have an easier time plugging it into the second one, okay? As we plug this in, just be really careful. Negative 6 squared is a 36. Then tack on that negative. That's a negative 36, okay? And then here, negative 2 times the negative 6 is a plus 12. And then the minus 7. Be really careful as you plug those things in, especially with that x squared. You have to square it and then apply the negative. It's like times a negative 1, okay? So let's see, that's a negative 24. Minus 7 is a negative 31. And I plug the 2 in, and once again, let me take it off to the side here. It's 2 squared versus 4, then apply the negative, so that's a negative 4. Minus 4 minus 7, that's a negative 8. Minus 7 is a negative 15. And there it is, two separate, distinct ordered pairs, okay? If I look at this one, same kind of thing. One of these is already solved for y. In all the previous examples, they were both solved for y, so it was like, hey, set the equations equal. Well, that's okay. You only need one of them solved for y, and this one's solved for y, so I can plug that in for y in the second equation. Okay, it's just a matter of I have to move less stuff around. I just get to combine like terms right out of the gate. Okay, so for this one, let's see, that's going to be a negative x squared plus 5x plus 3, and then the minus 3 equals 3x squared. Okay, so I substitute that guy in, and now I have to get everything on the same side. Because almost everything's on the same side already, I'm going to subtract the 3x squared from each side. Okay, over here, these are already on the same side, so I can just combine like terms. So here I get a negative 4x squared plus 5x. Those 3's actually cancel out, equals 0. And now I want to solve this one. This one can still be solved by factoring. It's just greatest common factor. So here I would factor out the x, leaves me the negative 4x plus 5. And now set each factor equal to 0. X equals 0. Negative 4x plus 5 equals 0. And now solve each. This one's already solved. This one I have to subtract the 5. And divide by that negative 4. So I get a positive 5/4. And now once again, I'm not done. I have to plug those back in and get the y values, okay? So again, two separate x values, two separate ordered pairs. And you just have to pick which equation looks easier to plug stuff into. So like, I'd probably plug stuff in to the second equation, looks the easiest. However, it's not solved for y. So maybe I want to rearrange this guy and go, okay, that's y equals 3x squared minus 3. And let's plug it into that. If I plug the, plus 3, If I plug the 0 in there, that gives me a 3. So that's one of my answers. And now plug the 5/4 in there. That's a little bit tricky. Let me take it off to the side here. 5/4 squared. So I square that. That's a 25/16. And now I multiply. That is a 75/16. I need common denominators. This is going to be a 48/16. And now I can add those guys up, and that gives me the 123/16. Okay? And since I left the x value as an improper fraction, I'm going to go ahead and leave this guy as an improper fraction. Let me scoot this guy over a little bit, give myself a little space. That's it. I get 2 separate distinct ordered pairs. Okay? And yeah, the second one wasn't pretty, but sometimes that's the kind of numbers we get. All right? Especially if we were modeling 2 real-world examples. Maybe we were looking at populations that follow a parabolic curve, and we want to know when are the 2 populations going to be the same. When are the attendance at some park going to be the same, okay? A lot of those things follow kind of peaks and valleys in terms of the way they're depicted mathematically, okay? So we're looking at 2 things that follow a quadratic function and seeing where those 2 things are the same, okay?